Hello everyone, this is Physics 30, Lesson 2 of Unit 2. We're talking about electric force. To represent electric force, we're going to go ahead and call this Fe, force electric. And we will hopefully remember our force of potential gravity equation. Remember in Physics 20 with Newton and all that good stuff, you'll remember that the gravitational potential force can be given as G m1 m2 over r squared. This is an inverse square law, famously discovered by Newton. Well, guess what? This is also a famous inverse square law, this time discovered by Coulomb. And it'll look very similar. K instead of G, Q instead of M, Q1, Q2, and there we go, over r squared. So it's a very similar formula. This time we're using charges, and we get an electric force. So let's read the question carefully. We have two metal spheres of equal charge. I'm going to assume that they're also of equal size. Let's go ahead and draw them on here, 1 and 2. Physics 30, we don't really deal with different sized spheres because we start getting into some interesting ratios. So we keep everything the same. Two metal spheres of equal size and charge given here. They are placed, we're told, 7.2 centimeters apart. Now I'm going to go ahead and change this right away to meters because I know ahead of time that I need meters. Pretty good habit to get into. So 0.072 meters. And notice that I'm going center to center. This is very important. Coulomb's law only works from the center. It assumes that the object has zero volume. It's assuming a point charge, which of course is not really true. The closer you get to the surface of a sphere, the more and more it'll start to appear or exhibit behaviors that would be indicative of a flat surface. You can think of yourself stood on the planet Earth. You're actually stood on a spherical object, but it doesn't feel like that. And that's why we can talk about gravity in terms of our experiences on planet Earth. We can think about it as being a uniform, constant, vertical force. But of course, that's not really the case. If you were a big enough object, you would experience this inverse law. So same deal here. We have a distance between them that hopefully is significant enough so we don't have to think about the sphere part. So I'm actually going to go ahead and I'm just going to get rid of the sphere completely, because once we've established that we're not talking about the surface of the sphere, we're not talking about inside the sphere, we're talking about a point charge effectively. Now we can use Coulomb's law. Coulomb's law assumes a point charge. So here we go, two charges, 7.2 centimeters apart, and we know the force. The force experienced by these spheres is 9. I'm going to put this on here as Fe. Force electric is 9.2 micronewtons. Well, micro is 10 to the negative 6. So there it is. Newton's third law tells us that there's an equal and opposite force. So if this sphere here is experiencing a force as a result of this sphere, that means that this sphere must be experiencing the same but opposite force from this sphere. So Newton's third law tells me that I can go ahead and put an arrow this way to represent the force. Oops, now these should be the same size. That was bad, wasn't it? So let's just get rid of that arrowhead and make it approximately the same size. Here we go. That looks about right. These two are the same. I'm going to go ahead and label it Fe. Over here is also 9.2 micronewtons. There we go. Equal and opposite. So, since I know the amount, I know the force electric, I can say this is equal to K, Q1, Q2 over R squared. Now, Q1 and Q2 are the same. So I'm just going to make this a little bit easier for us by saying K Well, now it's just Q times Q. Well, that's Q squared. So I'm just going to put it in like this. And of course, we're still over R squared. And I'm solving for Q. So I can go ahead and rearrange this for Q. So Q is going to be equal to, well, the force electric multiplied by R squared divided by K, and then I can just square root the whole thing. So Q, if you plug this into your calculator, is going to give you 2.303 ... lots of decimal places. So how many decimal places do I need? How many significant digits do I need? Well, I'm looking at my question. I've got 2 and 2, so it's going to be 2. So it's 2.3, and my calculator tells me that this is times 10 to the negative 9 coulombs. In other words, 2.3 nanocoulombs. That is my charge on each of the spheres. Okay, second example question is a ratio question. I love these. You'll definitely see one of these on the diploma, so you want to get pretty decent at doing these as best you can. Here we have an electric force between 2 point charges. We're going to call this F, and it's asking for a situation where both of the charges are going to be tripled and then the distance between them is halved. What is the new electric force in terms of F? Well, two ways of doing this. I'll show you the quick and easy way to begin with, but it's not a fail-safe way of doing it. It's pretty quick, so be careful. I recommend trying the second way as well, because the second way is more of an algebraic way of doing it. Anyway, here we go. We've got F. Okay, so we're told that F is our force, and of course we know that that is K, Q, we call it Q1, Q2 over R squared. Well, I'm just going to put the ratios straight in here. We're told that the charges are tripled, so 3. So we have a times 3. And then we also have another times 3. Both of the charges are tripled. And then the distance between them is halved, so 0.5. Now don't forget to square that. So if you go ahead and plug that into your calculator, very quickly, very easily, you get 36, which is correct. In other words, the force, the new force that will be experienced as a result of these changes is going to be 36 times that of the original. That's the quick and dirty way of doing it. Here's the more advanced way, if you like, of doing it. This is a fail-safe way of getting values, but there's a few more steps going on, so bear with me. I'm going to go through this, and I've probably done this in Physics 20 with you. It's a way to think about this in terms of ratios. It's a really good technique to get used to. Okay, so I'm basically going to make a bunch of statements. Then I'm going to substitute in some of these statements, cancel some stuff out, and I should be left with a ratio. So here we go. Statement number 1. I'm going to talk about force 1 and force 2. So statement number 1 that I'm going to make, I'm going to say that force 1 is my initial force, and I'm going to have a second force. That's the one I'm going to end up with. And these are not equal to each other. Okay, they're not equal because I'm making some changes to the system. So I can choose which one I want to do this to, but I'm going to put it as my force 1. I'm going to say that I have to basically multiply my force 1 by some integer, and that's going to give me a new force. I can also state this as K, Q, let's go ahead and call this QA1 and QB1 divided by R1 squared. That's my first force. And I'm going to make sure I keep my integer here. That's what I'm going to multiply it by. And that's going to be equal to my second force, which I'm going to call KQA2 QB2 over this new distance squared. Okay, so now I can come and I can continue writing my list over here. Here's my expression for the forces. I also now have expressions for both of my initial charges, QA and QB. These are the initial ones. These are going to become QA2 and QB2. Okay, now this is where I can look at my question and hopefully recognize that both of my charges are tripled. Okay, so what do I have to do to my charge? Well, my initial charge has to be tripled. So I can say that 3 times, let's just do this here in red, 3 times QA1 is equal to QA2, and 3 times QB1 is equal to QB2. Okay, final statement is going to be to do with the radius. So radius 1 is not equal to radius 2, because what do I have to do? Oh, I have to multiply it by, let's see, multiply it by, oops, I'm going to highlight that. I have to multiply it by a 0.5 because I'm going to halve it. So R1 is going to be multiplied by 0.5. Okay, so now I can start doing some substitutions. Okay, now remember, I'm trying to isolate this integer. That's what I want to know. And I've previously shown very quickly that it should be 36. So I can say that x is equal to k, let's put this in here, k qa2 qb2 over r2 squared. Let's put this in brackets here so we keep it simple. Divided by, because I'm just going to multiply, I'm going to divide this out, divided by k qa1 qb1 over r1 squared. Okay, hopefully that makes sense. Now, here's what we're going to do. We're going to start substituting in some of these formulas into this equation so that we end up with all A1s, all B1s, and all R1s. And hopefully we can start cancelling out and we should get ourselves a solution. So let's go ahead. First things first, I'm going to simplify this equation a little bit. I don't like having fractions over fractions, so let's go ahead and do that. I'm going to bring the R1 to the top here, so I'm going to say, let's go like this. We're going to go K, Q, A2, Q, B2. I'm going to bring this R1 all the way to the top of the equation to join at the top. So that's going to be R1 squared divided by, well, I'm going to keep my R2 squared underneath, my R2 squared, that stays there. But now additionally, I have this part of the equation that can join the R2 at the bottom. So I'm going to have K, Q, A1, Q, B1. Okay, good so far. All right, let's go ahead and start cancelling some stuff out. We can get rid of the K right away. That's nice. And now we can start substituting in. So I'm trying to get everything to be ones. So I'm going to recognize that QA2 up here, I have a statement for that. I can say that 3QA1 is equal to QA2. So I'm going to change this out. I'm going to switch this for this. I'm substituting it in. So let's do that. Let's substitute it in. So I'm going to say under here that K, actually, no, I've already cancelled out my K's. That's good. I don't have to worry about my K's. I'm going to say that QA2 is equal to 3 QA1, and I've swapped that out. Okay. Next thing to swap out is this one, Okay, so QB2, well, that's also equal to, surprise, surprise, 3 QB1s. Okay? R1s are already in the form that I want them in, because remember, I'm trying to keep everything in the first term, the first equation term. Okay, next one to cancel out will be my R2. This is the last the last term that's referring to the second equation. So I'm going to replace this with my statement from the beginning, which was that 0.5 R1 is equal to R2. So let me carry on writing everything out. The R1, oops, wrong color. The R1 stays the same, so R1 squared, haven't changed that. And then all over, well, QA1 is the same, QB1 is the same, and now I'm changing out this R2, which remember becomes 0.5 R1 squared. Okay. Well, let me take care of the square sign here. This square sign is referring to both the 0.5 and the R1. So I'm just going to multiply out my 0.5 by the square factor. So that will mean, so let me just get rid of that and change it to make it a bit more readable. I'm going to square my 0.5. So I'm going to leave my R1 to be still squared, but my 0.5 is going to be squared, so it gives me 0.25. Okay, now I can start cancelling out. This is the fun bit. I'm going to cancel out my R1 squared. Those both cancel out. I'm going to cancel out my QA1, gone, just leaving this 3. I'm going to cancel out my QB1s, leaving this 3. So look what I end up with. A nice set of integers, and fingers crossed it's the same as the 36 that I had to begin with. 3 times 3 divided by 0.25. Well, 3 times 3 is 9, divided by 0.25. Here we go. Happy days. It's 36. Yes, I know that was a long way of doing it. That was pretty arduous, but it's worth it. When you get more complicated ratio questions later on in your life, you're going to appreciate this technique. It's just a nice algebraic way of doing it. Using the substitution method will help you with so many cool things in physics. It's worth it. Okay, and this last example is classic conservation of charge question. We're going to take 3 metal spheres with given charges, and we're going to touch them together, and we're going to conduct those charges in a series of steps, and we're going to be asked to find a final charge. Now, key to this understanding is recognizing that we must have a total net charge initial, and that has to be equal to the total charge final. So this total amount of charge here, that's my initial charge. So I'm going to make a statement here and just say, let's go Q1 plus Q2 plus Q3 has to equal Q1 prime plus Q2 prime plus Q3 prime. Okay? And I can even go ahead and put those values in. I can say, what have I got? Negative 70 plus a plus 20 plus a negative 55. That must equal the total charge at the end. And so I'm going to have 3 steps, and I'm going to, by the end of the 3 steps, so let's label these step 1, and this is step 2. By the end of step 2, I need to know the final charge, and it should equal this total charge here. In fact, let's put the value in. Negative 70 plus 20 minus 55 is negative 105 coulombs. Incidentally, these numbers, these units, I think there might have been a little bit of a typo here. This probably should have been micro coulomb or even nano coulomb. Highly unlikely we're going to get 70 coulombs on a metal sphere. It's much more likely to be a tiny amount. But for the purpose of this question, it doesn't really matter. Let's just get rid of that. Doesn't matter. Let's just go with these whole numbers. Okay, so let's follow the sequence of events. We're told that Q1 and Q2 are touched together. So let's follow this process. This is 1 and 2, and they're touched together. I like to just draw this out like this, 1 and 2, touching like this. So now we have 1 and 2 here. Now, we're going to keep track of these charges. We've got a negative 70 and a plus 20. And so we're going to touch those together. So they're going to add together and give us a total charge. So negative 70 and a plus 20 gives us negative 50. But this charge is conserved, and then these spheres are split apart. So we need to divide this by 2. And so that gives us our new charge on sphere 1 and sphere 2. It's equally shared between them, which is why I've divided by 2. So I've got a negative 25 coulomb and a negative 25 coulomb. Sphere 3 over here, well, that hasn't changed because it hasn't touched anything yet. So this is still negative 55. Okay, step 2 is to now touch Q1 and Q3 together. So here's Q1, it's going to come all the way over here, touch Q3. And so we have sphere 1 and 3. Well, let's do the math. We have a negative 25 and we have another negative, this time of 55. Those are going to be added together, which is giving us 80. So that's a negative 80. But I have to divide by 2 because it's going to be shared between the two spheres equally. So this is going to give me a negative 40 and a negative 40 coulomb. And of course, sphere 2 is unchanged, so negative 25 coulombs. The question is asking what's the final charge of Q1? Well, we've just put that in. So the charge of Q1 is negative 40. So I can draw a nice ring around that. That is my answer. All that's left for me to do now is just verify this, just to double check. Remember that I needed to have the charge equal. So I had a negative 105 coulombs to begin with when I added up all of the charges to begin with. Now I'm going to do the same for my final, and it better be the same, otherwise I've lost charge and I've just broken a fundamental physics principle, conservation of charge. Can't go anywhere. Of course, assuming that this system is isolated, assuming that no electrons have drifted off into the air, which would normally happen, but we're making some assumptions here. So let's go ahead and add these up. Negative 40 plus negative 40 is negative 80, plus the negative 25. Surprise, surprise, it's negative 105. And that's confirming my conservation of charge. Now I've verified that this is true.